Honors Physics Lesson 4.3, Systems of Objects. Welcome, welcome, welcome. All right, so um, usually we're looking at objects, we're looking at them individually. But now what we're going to do is look at a couple of objects that are moving together. Ooh, fun continues. All right, so let's start off with something simple. So we got two boxes. They're sitting on a frictionless surface, and they both have different masses. If you push box A with a force of 300 newtons, and this is not a free body diagram, I'm just showing you that there's a force being applied over there of 300 newtons, then what's going to happen? What's the acceleration of the two boxes? So what we're going to want to do here is we want to draw these separately. So here's box A with a force, box A, 25 kilograms. And then here's box B with 50 kilograms. Alright, so what we're going to want to do is we're going to look at these as one large box, which is 50 plus 25 kilograms. So that gives us a total of 75 kilograms. Since the force is being applied to both of them, we have to reuse that force on both masses, right? Cool. All right, so now our net force equals our mass times our acceleration, so 300 equals 75 times A, so therefore A equals 300 divided by 75. So our acceleration is a nice 4 meters per second squared. Sweet. Easy enough. But what about how much force do these boxes exert on one another? So this goes back to Newton's third law. So what I like to do is I like to look at the larger mass. So that's going to be this 50 kilogram one right here. Because this is going to push back on the 25, and the 25 needs to push back with this. And we always have to be able to push this 50 kilograms, because if that force is less, then it's not going to be able to push the 50 kilograms. So the 50 kilograms is really what's exerting this large force. So what we're going to end up doing is looking at our mass, not a space here, and our net acceleration. So here's our mass, 50 kilograms. The whole thing is moving at 4, so that means that our force here, that it's pushing back over here, is 200 newtons. Alright, well now it says verify. Alright, so now we need to verify this. Again, that's not a free body diagram, this is just me showing you where the force is going. This other box here, box A, do that in red, it has a mass of 25. So if we do that same kind of idea, 25 times 4, we're looking at a force that is applying that way of 100 newtons, right? So when we look at our combined forces, 100 newtons plus our 200 newtons, that should equal our net force, which is 300 newtons. Yay, we verified it. Sweet. The other thing we could do is then just take this 25 and we could take that 100 newtons and divide it and see if that came out to 4, and it does. So we're good then that way. Alright, this next one is a little bit more tricky. So what we have here is these two boxes, and it's at rest, and there's a distance of 1.8 meters here, and that goes for both of them. Alright, so the first thing I wanted to tell you is that whenever we have a pulley system like this, we need to identify which way is positive and which way is negative. Because, right, gravity's pulling on them both down, but one's going to go up. So I always think the left side is negative and the right side is positive, so any time that we go like this or like this, that tells us which side is negative. So even though gravity is pulling on them both equally at an acceleration of 9.8, anything that goes clockwise will be positive, and anything that goes counterclockwise will be negative. All right, so we wanted to know how long it's going to take this box to hit the ground. Problem is, we need to know what the acceleration of gravity is, because this box A is going to be moving with box B. They're connected. So we need to find out how much the whole system is accelerating by, which shouldn't be too hard if we kind of apply some of our information that we had from before. So over here, we have a force, and that's going to be 2.5 times 9.8. So this is going to be our negative, I'll do color here, 24.5. It's negative because it's the left side. And then over here, we have 3.5 times 9.8. This one's going to be positive because it's on the right side. That's a really bad 3. I'm sorry. All right. So just like we did before, our net force equals force A plus force B. And if there was friction in there, we'd add friction too. I had all the forces for net force. So our net force here is negative 24.5 plus 34.3. So that equals, interesting, 9.8 newtons. What a weird quinkadink. All right, now this force equals our mass times our acceleration. Well, this is the total mass of our system, just like before. So 9.8 divided by 6 kilograms, and that gives us an acceleration of 1.63 meters per second squared. Sweet, but it doesn't want that. It wants how long it's going to take to hit the ground. So now that we have our acceleration, we can go back to our linear equations that we dealt with before and figure out the time it takes to hit the ground. Now, since it was initially at rest, this part of the equation doesn't matter. The delta y is 1.8 meters. That's how far it was in the air. That equals 1/2 of our acceleration, 1.63, multiplied by our time squared. So our time to hit the ground is about 1.48 seconds. All right, but what about this other one? So now, the first B, this should be BC, but anyways, this B right here is asking about the tension in the rope. All right, so it wants to know the tension in the rope, so how much this is. And the same idea goes that we did before. We're going to look at the first of our masses, the one that is the largest. And we're going to use that to figure out our net force, right? Because we have something that's pulling up here, and then we have something that's pulling down here. So if you start with the larger mass, you're never going to go wrong. At least in my opinion. In my opinion, is the only one that counts. No, really, no one likes me. Anyways, so this mass that we have going down is 3.5. And we need to multiply that by our net acceleration, which was 1.63. That'll give us our net force, which equals our force of tension plus whatever our force of gravity was, which is 294. Yes? Now, the tricky part here is, remember, anything that's left is negative, and anything that's going to the right is positive. So even though it's going up, we're going to consider that negative because it's going towards the counterclockwise direction. So that gives us a net force, or force of tension that equals 246.9 newtons, so 247. Cool. So that's the force of tension. And then the last part B is asking about the other side, right? So this one hits the ground, smack, ground. And this one goes up. But it doesn't just stop once it hits the ground. Now it has a velocity, right? It's accelerating in this direction at this 1.63. So it's going to go up. Eventually it's going to come back down because gravity still pulls on it. So we need to figure out that little extra that it's going. So it's definitely going to go up 1.8 meters. It was already at 1.8 meters. So it's going to go up at least 3.6 meters. Plus our unknown, right, our delta x. And what we need to do here is we need to go back to that time that we had from before. So that time tells us how long it was accelerating for. So our acceleration is 1.63. That equals how fast we ended up going minus it was at rest divided by our 1.48. And that gives us a velocity of 2.41. So it's going 2.41 meters per second when the other one hits the ground. So now gravity is going to affect it. The other one hit the ground. It's no longer acting in tandem in this whole system. Now gravity is the only thing that's pulling it down. The other one already hit the ground, so it's not going to pull it down anymore. So what we're going to do, we're going to go back over to our nice acceleration equation. 2 times gravity negative, and now it's going down. Delta y, that's going to be this little difference that it keeps going, which equals our velocity final, 2.41 minus, I'm sorry, I got that backwards. That's our velocity initial. Eraser. Velocity initial, or velocity final at the top of its height is 0. Right? So it goes up, it's like a parabola, right? So at the top here, velocity equals 0. Started off at that 2.41, and now velocity is 0 before it starts to come back down. So our delta y ends up being 2.296 meters. So it ends up being 3.6 plus our 0.296, and that gives us a max height of let's call it 3.9 meters.
Good afternoon,
Okay,
staff and
thanks.
students.
Goodbye.